Hey guys, welcome to chapter 12, and we're going to start out with the waves today. So this node set is on wave energy. What are the types of wave energy that travel in waves? So obviously, looking at the picture, we can think of waves as ocean waves, right, as an example. All right, so you know that pattern, the up and down pattern that happens with the waves. All right, so pretty much energy transferred in that way is what we're going to be looking at and focusing on. So what is wave energy? It's basically a disturbance that travels energy from place to place. And obviously it's going to be the particles in the substances that are moving around. So mechanical waves travel through a medium such as gas, liquid, or a solid. So an example, gas could be air, right, transmitting wave energy, like sound. All right, as I'm talking to you, my sound waves are traveling to your ears. Liquid water, all right, so obviously the ocean waves traveling, the energy traveling through the ocean waves. Solids also transmit waves. You feel vibrations, right, during an earthquake as an example. So a rope could be an example of that. You flip the rope and then the vibrations will go through the rope to the other side. And you can actually use a rope or string to talk to somebody through an old-fashioned telephone. All right, you talk through the cup basically, and the other person puts it up to their ear. Right, and we'll look at examples of that with sound. So how are mechanical waves formed? All right, there are vibrations in whatever medium they're traveling through. So a good example could be like a guitar string vibrating, causing the molecules of air to move. All right, like seen with the guitarist from AC/DC here. Right, so basically vibrations through air is what transmits sound. Okay, so there are two types of waves. The first type is the classic S wave pattern that we know, which is called a transverse wave. Right, so I think of S pattern transverse. Right, there is an S in the middle. Waves that move up and down, so an ocean wave is a classic example of this. Sound waves also travel in this fashion. All right, and the next type is compressional. All right, if you take a slinky, all right, which you know, and you compress it, and then the wave goes through it, left to right, all right, through it, in the direction the wave is moving, that's called a compressional wave. All right, so the energy moves back and forth through the slinky. Right, so that's also called a longitudinal wave. So compressional, longitudinal are the same thing, right? So if you hear that in some questions. All right, so parts of the wave. All right, so obviously a wave goes up and down. So what are the parts that we talk about? Okay, so in this picture here, you'll see the crests are the top of the waves. Troughs are the bottom of the waves. The middle line is called the equilibrium position, so that's if there's no wave energy being transmitted, it's going to be flat. All right, I always think of when the person passes away, the flat lining, all right, that's equilibrium position, all right, because obviously your heart stopping, all right, these waves would cease to actually continue moving up and down. Wavelength, distance from crest to crest, or trough to trough, right? So it's usually the same position of one wave to the next. So the easiest way to measure that is the top of the waves, the next top of the wave, or the bottom of the wave to the next bottom of the wave. Okay, and then also amplitude is distance from the top of a crest down to the equilibrium position. So that's how strong the wave is, all right? That's something we also look at. All right, so wavelength, we talked about. All right, frequency is the number of waves passing a point each second. All right, so basically we'll look at how often the wave is contacting a surface. So a shorter wave is going to contact the surface more often. A longer wave is going to contact the surface less often. All right, and we measure this in hertz, so that's wavelengths per second. Okay, so what happens to a wave as it travels? So the following different things can happen. Reflection, right? So I think of a mirror, right? It's a bouncing back, right? So the wave will hit the surface and then bounce off of it. Refraction is like a bending. So as it goes from one medium to the next, right, solid to a liquid as an example, or a liquid to a gas, it will change direction because the speed will change of the wave traveling. So refraction is an example of that. It bends when it changes from one medium to the next. Diffraction means basically to bend around a barrier, go around a barrier. So we'll look at that, what that does. And then interference is when waves interact with each other, and that's especially seen with sound. You get two singers that don't sing the same note, you'll definitely hear a difference, as an example. All right, so reflection occurs when wave hits a surface and bounces off of it or bounces back. That's why things have colors. All right, so when you look at a leaf like this, that's orange and yellow and red, the reason why you see it as that color, those are the colors that are bouncing back towards your eye. In colors, when obviously it's dark out, you can't make out colors, right? Because you need the light waves bouncing off the surface to see the colors on an object. So light waves hitting a mirror produce an image. Colors we see are the reflected light back to our eye, or a combination of certain colors back to our eye. An echo in a large room. Okay, so I hear an echo bouncing off the wall, right? And that's why auditoriums are designed the way they are, right? Trying to bounce the sound energy towards the audience, basically. All right, refraction is a bending of waves when they enter a new medium. So in this case, they're going from air to water. And you can see it looks like the ruler is bent, but it's really not. When you see the water from the side, what it does, the light actually reflects or refracts as it enters the water. And therefore, you see a bent image of the ruler. Okay, so caused by a change in wave speed. So light waves bend as they hit the water, changing the image to your eye. All right, so classic example, ruler in the water, or the pencil, sometimes they show in a picture. Also spearfishing, all right? That's why if you're a spear fisherman, you can't actually throw the spear directly at the fish where you're looking at. You would have to actually hit slightly bent from where that you're seeing that object. Otherwise, you're going to miss the fish completely. All right, diffraction is bending a wave around a barrier. So ocean waves bending around an island as an example, because the water gets shallow. Right here, it's deeper on the outside. So what ends up happening is where it gets shallow, the wave is going to slow down, and then the other areas it keeps going the same speed, so it ends up bending around the object. All right, and caused by a change in wave speed. So again, so some areas will slow down, some areas it keeps the same speed, and that's why you get that bending around the barrier. All right, interference is the interaction of waves and they bump into each other. There's two types that exist, either constructive or destructive. All right, so constructive, obviously they work together. Destructive, they work against each other. All right, so let's do this with sound as an example. So constructive interference, right, and this is a way a band, a chorus, an orchestra, you have multiple people playing the same thing. If they play the same exact note, what happens? You add up the two waves and you get a louder sound, and it sounds good. All right, so the waves actually help each other, increasing your amplitude, increasing your sound, and that's why a musical group right in sync with each other sounds great to your ear. On the other hand, a musical group that doesn't sound good, they'll have waves that aren't matching up, and the result is you get a crest meeting a trough, or a crest not quite matched up to the next crest. And what ends up happening is you hear interference. And interference can either be canceling out totally, or you'll hear a wave that's like a new note. And that's why when you hear that one person play the off note on the instrument, you know it. right? Because your ear is trained to hear the correct sound. And then once that other person plays a different note, it's not lined up, and we notice that you get destructive interference. Okay, so again, so constructive, adding up the waves to make a bigger wave, and then destructive, you add up the waves, and they're exactly opposite in this case, so they end up canceling each other out. That doesn't always happen. Again, it's more of the waves not meeting up, so you get a different wave at the end. All right, so that's it for wave energy, and I'll catch you guys next time.